Hey everybody, in this video we're going to look at the fundamental theorem of calculus, part 2. So here's the plan. We will briefly review the fundamental theorem of calculus, part 1, also known as the evaluation theorem. We'll review accumulation functions. Then we'll state and prove the fundamental theorem of calculus, part 2. Although, prove might be a little strong of a word here, so we're going to make as plausible as possible. It's going to be fairly rigorous, but there's going to be a little bit left over that would need to be proved rigorously. So let's recall the fundamental theorem part 1, also known as the evaluation theorem. So the idea here is, if you have a continuous function on a closed interval, and then you have another function whose derivative is equal to that function for all x in the interior of the interval, in that case, what we would say, by the way, is that f, capital F, is some antiderivative of little f. It's a function whose derivative is little f. So in that context, we know that the definite integral of little f from a to b is actually equal to the value of the antiderivative f evaluated at b minus the antiderivative of f evaluated at a. So for example, since the derivative of 1/3 x cubed is x squared, that means 1/3 x cubed is an antiderivative of x squared. We would know that the definite integral of x squared on an interval from a to b is actually equal to the value of the antiderivative at each endpoint and then subtracted. And then you'd get 1/3 b cubed minus 1/3 a cubed, which is indeed a result we saw in a previous video about the signed area under the graph of x squared. So what are accumulation functions? So this is the name we're going to give to certain functions that are constructed by taking definite integrals of other functions. So for simplicity, we'll suppose that f is continuous, and it's possible to define these for functions that have a certain number of discontinuities as well, but let's just for simplicity say that we're dealing with a continuous function on R, and we're going to define the accumulation function f by setting capital F of x equal to the integral from some argument a to a variable x, and then we integrate little f. Now, this is the so-called integrand function. The integrand is the thing that appears inside the integral sign. So there's our sort of original function that we're using to construct our accumulation function. And we could plot the graph here. And then we need a so-called anchor argument. This would be the argument where all integrations begin. So we can change x, but we always start our integration at a. And the argument of our accumulation function appears here, and it would appear in the upper limit of integration in the integral symbol. So as x changes, the value of this function changes. So if you pick a particular x, the value of capital F of x is going to be this signed area under the graph of the integrand function. And as you change x, that value can change. Let's get a dynamic picture with the help of Desmos. So what we'll do is we will take a particular function here. So this is our integrand function, whose definition isn't really relevant here. We can hide it away in the folder with gadgetry in it. So we've got a function f defined here, and then here's the graph of our integrand function. And here's where the integrand function shows up in our definition of the accumulation function. Now in this case, we chose the anchor argument to be 2. And here you can see the anchor argument labeled in our graph. Then we have the definition of the accumulation function right here. And you'll notice that Desmos provides the graph. Here's a nice graph of our accumulation function. We should point out that we must use a variable of integration other than x. So notice in this integral in our Desmos worksheet, I used the integration variable t because x is already used up as the upper limit of integration. Here is a slider for an argument x, and so if we want to see different values of the accumulation function at different arguments, we can move this slider or the point that's plotted on the graph. So here we'll just move in and drag the argument around a little bit, and we can see the accumulated area and the value of the accumulation function plotted along the graph of A. And let's just pause here to take a look at a more or less randomly chosen argument. This argument is 4.13, and the corresponding value of the accumulation function is about 5.8. And where does that number come from? So what we can do is we can approximate this number. Here's a trapezoid whose area should be about equal to the value of this accumulation function at 4.13. The base is 2. This height on the left side is 2, and this height on the right side is 3.5. So we can easily find the area of this trapezoid, and using the standard technique for doing so, we get about 5.5 for our area, which is about equal to 5.8, but smaller than what you would expect from the graph. So this all looks reasonable. It looks like the accumulation function is doing what we expect it to do. Now here's a little activity. Let's graph the derivative of this accumulation function. So we'll enter a cell in Desmos here. So we're going to plot the graph of a prime of x. And we select this, and lo and behold, this graph sure looks like the original graph of the integrand function. So the very natural question here, are these functions the same? Put another way, when you take a function, put it inside the integrand of an accumulation function, then take the derivative of that accumulation function, do you arrive back at the same place? And the answer to that is yes. So let's do the calculation and show that this is generally true. So we are going to answer the question, what is the derivative of an accumulation function? Here's our setup in the form of a picture, giving us the meaning of capital F evaluated in an argument x as assigned area. And so now we're going to take the derivative of this accumulation function. This is the standard definition of the derivative. We're going to set up a secant slope, and we're going to look at the limit of this as h goes to 0. So that's standard stuff right there. And so we're just going to factor out the h from the denominator, and we'll be looking at the limiting value of this expression right here. Now let's plug in the definition of f as an accumulation function here. So we're going to have this integral for f of x plus h and this integral for f of x. And now what does this difference really mean? So we can draw a quick picture of this. Here's f of x plus h, which is this integral right here, the integral from a to x plus h. And here's f of x, the integral from a to x. And when we take this difference, it's pretty clear from the picture that the difference should be the integral from x to x plus h of the integrand function. So that's what we expect this quantity inside the square brackets to equal. But let's sort of derive this fact with a little more rigor, because we have some properties of integrals which are going to really be handy here, and it's useful to test drive them. So first of all, remember that we can swap the limits of integration as long as we change the sign of the integral. So we're going to actually integrate from x to a and change that sign to a plus in front. And now we'll notice, by just switching the order and then observing that these arguments are the same, we have an interval combination law that allows us to rewrite the sum of these two integrals simply as the integral from x to x plus h. So that's an interval combination law in action. And so what we see then is that the expression we expected is in fact the simplification of f of x plus h minus f of x. So here is a much simpler version of our formula for the derivative. And now we want to understand what this limit is. So first of all, another picture will help us get our bearings. Here's an example of what we might be facing. Say we want to integrate from x to x plus h, so we're looking for this area right here. But we're going to notice that there's a rectangle whose width is h and whose height is the value of the integrand function at x. So if h is pretty small, close to 0, then the hope is that the areas of the region we're integrating and that rectangle should be more or less equal. They should be close to each other when h is small. And so when we divide through by h, it means this expression that we care about is pretty close to f of x. And as h gets closer to 0, the hope is then that this will wind up having a limiting value of f of x. So this is a heuristic argument as to why we should expect the derivative of an accumulation function to return the integrand function. But once again, we're going to be a little more rigorous about this. So we need to think about a property of continuous functions. Suppose that f is continuous, and we're going to just imagine the domain is R to simplify things here. But so we have a continuous function, and for a fixed argument x, so we're going to anchor an argument x, and then we're going to look at a function of h. So what is h? H is sort of a distance you move away from x, and we'll let mu lower star of h be the minimum value of f on the interval with endpoints at x and x plus h. And similarly, we'll define mu upper star to be the maximum value of f on the interval with endpoints at x and x plus h. So we're going to have a picture here. Don't worry, because that's quite a definition that looks rather hairy. But if you had your graph of the function f and you anchored your argument x, now choose some non-zero value of h. So suppose you choose h to be a positive number. So you step that far in that direction. There's x plus h. And so the game is you ignore everything except the graph of f from x to x plus h. And now that's a continuous function on a closed interval, and we know the extreme value theorem says that there should be a maximum and minimum value. So here would be the value of mu lower star of h, and here would be the value of mu upper star of h. So this is simply a picture of what it means to be looking at mu upper star and mu lower star of h. We've anchored x, and h is how far away. You're going to sample arguments, and on that closed interval, you look for the minimum and maximum values. If you chose h to be negative, say, you'd move off in this direction by a certain amount, and again, you ignore the rest of the graph, and you look for the minimum value. It occurs at an endpoint in this case, so this would be the value of mu lower star of h, and this would be the value of mu upper star of h. Now what we want to do is imagine what happens as h approaches 0. Watch carefully at, so we're going to actually let h approach from both the right and the left. So you have to imagine that for all these different choices of h, as h goes to 0, where you locate the maximum and minimum values gets more and more constrained. And so you should be able to imagine that your options force both the maximum mu upper star and the minimum mu lower star all to converge to the same place. Mu upper star of h and mu lower star of h converge to the value f of x as h goes to 0. So once again, watch what happens. Just try to imagine where mu upper star and mu lower star occurs for each of these values of h, and you'll see that as h goes to 0, the options really shrink, and ultimately you approach f of x. So this is a consequence of the continuity of f. This is where the continuity of f really kicks in, and this is what allows us to prove the fundamental theorem. So we'll take this lemma back, and now we'll imagine here's where we left things. We were trying to evaluate this limiting value. So the thing to notice is that for a given choice of h, you step away from x, and you'll have mu upper star, the maximum, and mu lower star, the minimum. And so what we have is, here's the value we care about, this integral right here. So this is the signed area that we actually care about. But we'll notice that there's a rectangle whose area then is the base h times the height mu upper star of h. That area has to be larger. And there's another area of a rectangle. If you use mu star as the height, then h times mu star of h is going to be less than or equal to that quantity. And now we'll divide through this inequality by h. By the way, I should point out that we've assumed h is positive. You'll have to work a little arithmetic to make sure that this proof still works when h is negative. Maybe you'll want to think about the case when the value of f is negative as well, but the essential property is still going to work. And so what we have here is an inequality. 1 over h times the integral from x to x plus h is trapped between mu lower star of h and mu upper star of h. Well, a moment ago, we noticed that the limit of mu lower star of h goes to f of x, and the limit of mu upper star of h is f of x as well. So the squeeze theorem kicks in. And the limiting value of the expression we care about must also be f of x. And there's our proof. The derivative of the accumulation function at the argument x is equal to the integrand function evaluated at x. So this is the fundamental theorem of calculus, part 2. The idea here is that if you have a continuous function on some open interval, then for every anchor argument that you choose from that interval, you build this accumulation function. That accumulation function is differentiable, and the derivative of that accumulation function is just the original integrand function. In other words, when you use a continuous function as the integrand of an accumulation function, the resulting accumulation function is differentiable, and the derivative is precisely the integrand function. So, if this sounds familiar, in fact, the evaluation theorem, which is what we called the fundamental theorem part 1, and now the fundamental theorem part 2, they're actually two sides of the same coin. They're very much related. They're almost saying the same thing. They're saying the same thing sort of in opposite directions. So the evaluation theorem tells us that you can use antiderivatives to evaluate definite integrals. But you also have the option of using definite integrals in the guise of accumulation functions to create antiderivatives. So they're really exploring two different parts of the same phenomenon. So there are a few more things we can say about the fundamental theorem. We'll assume f is continuous, and we'll notice that from f we may build infinitely many different accumulation functions. It all depends on which argument you use for your anchor argument. So we could build all these different accumulation functions. And what the fundamental theorem of calculus tells us is that it doesn't matter which of these anchor arguments we use. When we take the derivative, we're going to recover the original function, the integrand function. What does this mean? It means every accumulation function of f is an antiderivative of the integrand function. Now, there's a caveat here. There's really a detail that we need to worry about. This statement's true only provided the domain of f is a single open integral. If the domain of the integrand function is the union of two or more disjoint intervals, then you might have a problem. So for example, here's the reciprocal function. We could use the reciprocal function to build an accumulation function. Let's call it f. And so we'll use the anchor argument 1, and when you plug in an x, then you integrate from 1 to x, you're going to get your value of the accumulation function. But there's a vertical asymptote at 0. And in fact, you can't integrate from 1 across the vertical asymptote. So x can never be negative here. In other words, the domain of this accumulation function is actually the open interval from 0 to infinity. Well, the domain of an antiderivative of the reciprocal function has to be the union of the interval from negative infinity to 0 and the interval from 0 to infinity. What does this mean? It means it's not possible to express an antiderivative of the reciprocal function as an accumulation function. So in fact, the domain of an accumulation function is always a single open interval. Therefore, any function with another type of domain can't be an accumulation function. So accumulation functions are very special, and one of the ways they're special is that they can only have one type of domain, namely an open interval. So there are a whole bunch of functions that don't have such domains, so they couldn't possibly arise as an accumulation function. So for the rest of this discussion, we'll assume that the underlying function does in fact have a single open interval for its domain, in which case it's true that every accumulation function is an antiderivative. So if that's true, we should expect all accumulation functions of f to differ from each other by a constant. If they're all antiderivatives, they should all differ by a constant. So let's look at that calculation. Suppose you built two different accumulation functions from the same integrand, and you just used different anchor arguments. And so you could ask yourself, what is the difference in value between these functions as a function of x? So we'll use the definition of each accumulation. And then we'll notice, we've seen this reasoning previously, so we can flip the limits of integration in the second integral using the swap law. And then we can combine, and we get the integral of the original integrand function from a to b. But a to b have been anchored. These are constants, and so this whole value is a constant. This is a constant. So the difference between these two different accumulation functions is just a constant, whatever this signed area is between the arguments a and b. Here's a question you could ask. If every accumulation function is an antiderivative, is it true that every antiderivative is an accumulation function? And the answer to this is no. So how can we show this? It's actually pretty easy. fact, every accumulation function has at least one zero, namely the anchor argument. So for example, if this was your definition of an accumulation, you'd notice that automatically f of a had to be 0 because you're integrating from a to a. Every accumulation function has at least one zero. So here's a function, sine x plus 3. But we know that this function has no zeros. So if we take its derivative, we get cosine. So where does that leave us? The function f is an antiderivative of the cosine function. But also, f can't possibly be an accumulation function of cosine. It can't be an accumulation function at all because it has no zeros. So every accumulation function is an antiderivative, but not every antiderivative is an accumulation function.